Hi, we are Beatrice, Brian, Rachelle, and Kay Den from 23S6G, and today we'll be sharing about the history of the atomic model. Overall, we'll be talking about 6 different atomic models. The first one being the ancient model. The ancient atomic model was proposed by Greek philosophers Leucippus and Democritus in the 5th century BCE. It was the start of atomism, the philosophy proposing that the physical universe is composed of fundamental indivisible components known as atoms. The Greek philosophers speculated that the world essentially consists of myriads of tiny indivisible particles, and they theorized that the observable properties of everyday materials could be explained either in terms of the different shapes of the atoms which they contain, or the different motions of these atoms. In their version of the atomic model, atoms were considered the smallest division of matter. They theorized that the only two things the universe consisted of were atoms and void, which was the absence of matter. In their theory, there was only one type of atom, and the differences in physical properties of objects were attributed to the different combinations and shapes of the atoms. The parts of this theory that have been proven true by today's standards are that matter is made up of atoms, and atoms are the smallest particle of an element that can exist on its own in nature. Furthermore, differences in arrangement of atoms can lead to differences in physical properties. Based on the knowledge of the atom that we have today, we now know that there are many different elements, and atoms can be further divided into subatomic particles, such as electrons, protons, and neutrons. And differences in the physical properties of objects are also attributed to the differences in the elements they are composed of. Moving on, I will now be talking about the solid sphere model. It was proposed by John Dalton in 1803, and was also known as the billiard ball theory. John Dalton was also significant for his experiments which proved that gases consist of atoms. He also proved the existence of different elements through some other experiments. In Dalton's atomic theory, he proposed that all substances were made of atoms, and atoms are the smallest particles of matter. They cannot be divided into smaller particles created or destroyed. He also proposed that all atoms of the same element are alike and have the same mass. He theorized that atoms join together to form compounds, and a given compound always consists of the same kinds of atoms in the same proportions. Dalton thought of atoms to be small, solid hard spheres with no internal parts, and as such, he modeled them using wooden balls. The improvements that Dalton made from the previous atomic theory was that he acknowledged the presence of different types of atoms, and also acknowledged that compounds consisted of different combinations of atoms of various elements. However, the limitations are that there was still no mention of the existence of subatomic particles.
Now I will be sharing about the plum pudding model. The model was first proposed by J.J. Thomson in 1904, but it had to be abandoned in 1911 in favor of the Rutherford atomic model. The plum pudding model explained that electrons are negatively charged particles and that atoms have no net electric charge. According to the model, atoms were spherical in shape and consisted of negatively charged particles floating in a positively charged region, and atoms were electrically neutral, with the positive charge in the atom uniformly distributed. Some limitations to the model was that it did not mention the presence of the nucleus in an atom, as the positive charge is uniformly distributed throughout the atom. It also failed to explain Rutherford's goat scattering experiment, so it had to be abandoned.
So now we are going through Rutherford's atomic model, which is also known as the nuclear model. For the discovery, Rutherford performed an experiment where he bombarded gold foil with fast-moving alpha particles. So through this experiment, he found that a small percentage of alpha particles were deflected at large angles, and some even redirected back to the source, which was unexplainable at that point in time. So he concluded that all of the positive charge and the majority of the mass of the atom must have been concentrated in the nucleus, which was the center of the atom. For the features, he mainly found that the protons and neutrons are located in the nucleus, which is at the center of the atom, and that electrons will revolve around the nucleus and occupy most of the volume of the atom, as shown in the diagram on the right. However, this model also has its shortcomings, as it did not completely address the nature of the electrons and the way in which they occupied the space around the nucleus. Because if they revolve around the nucleus, there will be a point where they move closer and closer to the nucleus, ultimately merging with the nucleus, which will make the atom very unstable. And hence, this atomic model also does not explain the stability of the atom.
Moving on, we have the planetary model of the atom by Niels Bohr. So its history. It was created by Niels Bohr in 1913, and it is a refinement over Rutherford's model of the atom. Its features. It featured electrons which revolve around stable, discrete orbits surrounding an atomic nucleus. Each discrete orbit has a main energy level, and electrons can gain or lose energy by jumping between various orbits. Now its improvements. It involved the quantization of electron orbits, where each electron orbit can now be described by a main energy level. It also forsaked any attempt to explain radiation using classical mechanics. Lastly, it was also able to explain Rydberg's formula for the spectral lines produced by smaller atoms such as hydrogen. However, it had various shortcomings. It was limited in terms of the size of the atom which it could describe. It could not predict the spectral lines of larger atoms. It failed to explain the Stark and the Zeeman effect regarding spectral lines, or the effect of an electric field and an electromagnetic field on spectral lines. Lastly, it also violated Heisenberg's uncertainty principle. Last but not least, we have the quantum mechanical model of the atom by Erwin Schrödinger. Its history. It was created by Erwin Schrödinger in 1926. It is a refinement over Bohr's model of the atom. Its features. It used mathematical equations to describe the probability of finding electrons in various positions surrounding the atomic nucleus. Here, no exact electron path is defined. Instead, it consisted of a nucleus surrounded by an electron cloud, which could be further divided and subdivided into principal quantum shells and subshells. Its improvements. It is the most accurate model of how an atom actually works. Here, energies of electrons can be accurately calculated using the Schrödinger's equation. Lastly, it also does not violate Heisenberg's uncertainty principle.
In conclusion, the model of the atom has gone through many iterations, illustrating that science is not always exactly accurate, and there will always be room for improvements and new discoveries. Thank you for listening to our presentation.
Good day, everyone. Today, we'll be sharing our findings about the spectroscope with regard to how and why it works. Here's a brief run-through of what we'll be going through in this presentation. So, what is a spectroscope? A spectroscope is an instrument employed to measure the chemical composition of a substance, thereby discovering unknown substances through the identification of chemicals found within them. This process utilizes the separation of visible white light to determine properties such as light intensity, frequency, and atomic makeup of the substance. Naturally, the remarkable abilities of the spectroscope lend to its extensive use in many fields, from astronomy to numerous branches of chemistry. Ever since the discovery of the spectroscope, it has aided in innumerable breakthroughs, from discovering the behavior of the black hole to discovering many of the elements in the periodic table, rendering it indispensable in deepening our understanding of the universe. Let's briefly talk about the history of spectroscopy. In 1802, William Hyde Wollaston built a spectrometer that included a lens to focus the sun's spectrum on a screen. Upon use, Wollaston realized that the colors were not spread uniformly, but instead had missing patches of colors. Then, in 1815, Joseph von Fraunhofer used a diffraction grating as the source of wavelength dispersion. The interference achieved by the diffraction grating both improves the spectral resolution and allows for the dispersed wavelengths to be quantified. This version of the spectroscope is very similar to the one we made in class in terms of complexity. But moving on, further studies by Kirchhoff and Bunsen demonstrated the great utility of spectroscopy in chemical analysis. By systematically comparing the sun spectrum with a flame or a spark spectra of salts and metals, they made the first chemical analysis of the sun's atmosphere. Also, in 1861, they discovered two alkali metals, cesium and rubidium. Because someone questioned about this discovery in class, I'm going to explain a tad bit more about it. On May 10, 1860, while analyzing the spectral emissions from spring waters known to be rich in lithium compounds, Bunsen spotted a new sky blue signature in the spectra in addition to the expected light from sodium, lithium, and potassium. He and Kirchhoff realized it belonged to a new element, which he dubbed cesium, which is Latin for sky blue. The following year, Bunsen and Kirchhoff observed the presence of yet another alkaline metal with a dark red spectrum, hence the name rubidium. Since then, remarkable developments in spectroscopy have occurred in instrumentation, achieved largely through advances in electronics and manufacturing technology. Direct reading, automatic recording, improved sensitivity with good stability, simplicity of operation, and extended capabilities are features provided by many commercial instruments, such as this machine on the left by Thermo Fisher Scientific and the software on the right by Shimadzu.
So, how exactly can spectroscopes perform this task? The spectroscope is made up of three main parts: a slit, diffraction grating, and a detector. The slit allows visible light to pass through and reach the diffraction grating, where light is split into several colors of varying wavelengths as a spectrum with absorption lines. The sample obtained contains various pieces of information that help to identify the chemicals within the substance. This can be seen with a viewing port, but a detector is required to obtain the accurate numerical wavelengths of the elements, which are usually in nanometers. Now, we will be explaining how the source used works. Every element has some sort of a fingerprint of its own that can be used to identify it, due to its unique properties. This is due to the differing amounts of energy absorbed or released when an atom switches between its ground state and its excited state. The current model of atom that we study, with the principal quantum shells 1s, 2s, 2p, and more, reflect the atom in its ground state, when all electrons are in the lowest possible energy level. Atoms move from ground state to excited state through absorption of energy, and from excited state to ground state through releasing this extra energy absorbed in the form of photons, also known as emission. The exact difference between the two energy levels can be determined as the atom will only absorb or emit that exact amount of energy, thus only absorbing or emitting photons at that energy. This can then be seen by the absorption or emission lines created on the sample when compared to the atomic spectrum. Here are some of the different forms of spectroscopy and how the sources are obtained, as well as the information gathered from them. As the name suggests, X-ray spectroscopy utilizes X-rays to excite the electrons, and the analysis of diffraction patterns can determine the elemental composition and chemical bonding of a substance. As for flame emission spectroscopy, the heat from the flame is used to emit certain wavelengths of electromagnetic radiation from the substance when it is vaporized, creating emission lines on the sample obtained. On the other hand, in atomic absorption spectroscopy, lamps are used to excite the atoms, and when they transit from ground state to excited state, absorbing certain wavelengths of light, absorption lines are created. Visible and ultraviolet spectroscopy is sometimes used as atoms are able to emit and absorb visible light, creating similar results to flame spectroscopy. This is often used to measure purity, concentration of protein, DNA levels, fluorescence, and more. Infrared spectroscopy relies on the fact that molecules absorb different frequencies depending on their chemical structure and interatomic bond vibrations, thus being able to determine the bonds present in the substance. Lastly, nuclear magnetic resonance spectroscopy is often used for analyzing organic compounds as it exploits the properties of certain atomic nuclei to determine both the chemical and physical properties of the atom. Thus, extensive information, such as the functional group or even molecular environment of a molecule, can be found through this method of spectroscopy. Now, we will explain the diffraction gratings in greater detail. In the 1660s, they used prisms, which allowed light to exit as a spectrum due to refraction. However, a prism absorbs some light, resulting in slight inaccuracies. Hence, diffraction gratings are currently used as they offer improved efficiency and do not absorb any light. There are two types of diffraction gratings. Firstly, a reflective one where light splits into its colors and is reflected. This is essentially thousands of narrow lines root on a glass surface, similar to a CD. Next, transmission diffraction grating is where light diffracts into its constituent colors and passes through. This way, no photons are missed during analysis, which may occur when refraction is used instead. Another benefit is that the diffraction gratings can be used for UV wavebands, while prisms are opaque to UVs. We will now briefly discuss how the sample is analyzed. They are often analyzed with functional data analysis and chemometrics, with extremely complicated methods that we will not delve into. The basics are analyzing the location of the lines, the width of the lines, and the wavelength of the photon associated with that color. This will thus determine the energy difference due to the equation shown here, where h is Planck's constant and c is the speed of light.
A hydrogen atom is very simple. It consists of a single proton in the nucleus and one electron orbiting the nucleus. When a hydrogen atom is just sitting around without much energy, its electron is at the lowest energy level. When the atom absorbs energy in the form of light, the electrons in the atom are able to jump up in energy levels depending on how much energy it absorbs. It is important to note that electrons must jump from one energy level or another and never in between, and that a discrete amount of energy, no more, no less, is absorbed to move the electron from one energy level to another. Knowing this, the energy that the electron needs in order to jump up to a certain level corresponds to the wavelength of light that it absorbs. Said in another way, electrons absorb only the photons that give them exactly the right energy they need to jump levels, and hence it is possible to view through spectroscopy that in the visible part of the spectrum, hydrogen absorbs light with wavelengths of 410 nanometers violet, 434 nanometers blue, 486 nanometers bluish-green, and 656 nanometers red, and each absorption line corresponds to an electron energy level jump. This is visible in the diagram in the top right hand corner, which shows the different colors and and how many levels each of them are able to jump to, and also visible in the bottom right diagram, which shows the relationship between the electron jumps and the specific wavelengths of light that the atom absorbs. Just as electrons are able to absorb light and hence absorb energy and jump in energy levels, electrons are also able to lose energy and drop down to lower energy levels. When the electron drops down between levels, it emits photons with the same amount of energy and the same wavelength that it will need to absorb in order to move up between those same levels. This is why hydrogen's emission spectrum is the inverse of its absorption spectrum, as mentioned just now. The highest energy and shortest wavelength light is hence given off by electrons that fall the farthest. On the top left, you can see a diagram which is a simple model of the hydrogen atoms showing 4 of the many possible drops the electron could make when it emits light. And in the bottom right, you can see the relationship between the electron drop and the specific wavelengths of light that the atom emits. When the electron drops down from one energy level to another, it emits a photon with a specific energy and hence a very specific wavelength of light. The further the drop, the shorter the wavelength and the higher the energy of the photon. The illustration shows a set of drops that correspond to emissions of visible wavelengths.
Now, I'll talk about the variations on spectroscopes and spectrums. Firstly, there's a continuous spectra, which is the starting point of many other spectrums. Continuous spectra is a continuous spectrum with brightness varying evenly from color to color. In an ideal continuous spectrum, there are no missing colors. A black body curve on the right is a continuous spectrum displaying the band of light emitted solely due to surface temperature. It is the starting point of many other spectrums. Now I'll talk about the absorption spectra. An absorption spectrum looks like a continuous spectrum, but with some colors significantly dimmer than others, or nearly missing. The black lines are known as absorption lines, and it's explained previously in other sections explaining the spectroscope. And the emission spectra is the opposite of absorption spectra. It instead reflects the wavelength of light emitted when electrons drop in energy level. It's particularly useful for studying clouds of hot gas. The difference in brightness of different emission lines can tell the temperature and density of the gas and the relative amounts of different elements in the gas. A transmission spectra is a type of absorption spectra. When starlight passes through the atmosphere of a planet, for example, some of the light is absorbed by the atmosphere and some is transmitted through it. Dark lines and dim bands of light in the transmission spectrum, you can see on the right, correspond to atoms and molecules in the planet's atmosphere. The amount of light transmitted also depends on how dense and warm the atmosphere is. Last but not least, reflection spectra. It shows the colors that reflect off a surface. It can be used to study rocks, soil, ocean water, ice caps, mineral deposits, forests, farmland, dust storms, volcanic eruptions, and even wildlife. You can also study what surfaces of planets, comets, moons, and asteroids are made of, so it's especially useful to astrologists. The patterns of colors that a material reflects depends on not only what colors it is absorbing and transmitting, but also on many other factors, like roughness, shape, and orientation, and hence it is not very accurate. Lastly, do you know that the human vision is a spectroscope too? Being able to recognize and infer about different materials make our everyday color vision a rudimentary form of spectroscopy. We're able to tell the difference between everyday objects and materials by the way they interact with light, which is literally what spectroscopy is. These are our references. Thank you.
Hi guys, this is Chem Group 3 and we will be presenting on the wave function and quantum mechanics. So what is the wave function? It is denoted by the Greek letter psi, and it's the sum of all possible states of a particle whose coefficients are the probabilities of the states. So let's say you have a particle that has a 0.75 chance to be at A and a 0.25 chance to be at B. So psi will be equal to 0.75 A plus 0.25 B. It's a mathematical description of the properties of a particle. a so-called probability amplitude, which if you look to the graph at the right, that's a probability amplitude of a certain particle. And based on Bond's statistical interpretation, properties of particles are probabilistic. And the square of the wave function is equal to the probability density function. So what can you do with this wave function? If you apply certain operators to the wave function, you can get the probability density function of that property. So for example, let's say we have an electron and a distance from the nucleus. And so if I were to graph sine squared against the distance from the nucleus, you notice that since the position operator is directly proportional to sine squared by looking at the integral above the graph, hence we will get sine squared graphed against distance from nucleus is a probability amplitude. And there are other operators like the Hamiltonian operator and the momentum operator. I will now be passing the time on to Jonathan, who will be explaining the collapse of the wave function and the Schrödinger wave equation.
Moving on to the collapse of the wave function, based on the Copenhagen interpretation, the particle will exist as the sum of all possible states when it's unperturbed. However, when a measurement is made, the wave function will then collapse into one of its possible states. So as we can see in the meme over here, what scientists have actually done was to place a detector in each of these slits to see which slit the particle actually went through. However, when the particle went through the slit, the detector actually collapsed the wave function, and hence we notice that the particle is displaying so-called particle properties over here. However, in this case, when there was no detector in the two slits, the so-called particle was able to display its wave properties, and hence we are able to visualize the diffraction over here. So on to the Schrödinger wave equation, it actually denotes how the wave function evolves through space and time. And if one would like to acquire the wave function in its mathematical form, it would be necessary to solve the Schrödinger wave equation. And since the Schrödinger equation is a linear differential equation, the so-called complete solution is actually a linear combination of all the possible solutions. And this also corresponds to what was mentioned earlier on how the wave function is a sum of all the possible states. So this is actually the superposition principle at play as well.
Next, I'm going to be sharing on the ontology of quantum mechanics. Ontology is basically the philosophical study of being on the most fundamental level. So the difference between quantum mechanics and classical mechanics is that classical mechanics is deterministic, whereas quantum mechanics is probabilistic, which means that in quantum mechanics, we incorporate randomness into our approach. Second difference is that in classical mechanics, particles and waves are different, whereas in quantum mechanics, you have the wave-particle duality, which means in classical mechanics, things are either particles or waves, whereas in quantum mechanics, you consider things both a particle and a wave.
Last but not least, we'll be talking about the birth and history of quantum mechanics. Regarding the interpretation of quantum mechanics from the 1900s to the 1930s, there were many intense discussions among scientists, and these scientists could all agree on how detailed quantum mechanical models could be arrived at, as well as how the calculations were done. And these calculations could compare the experimental results with the theoretical calculations. Furthermore, intermediate results of a calculation can also determine the physical processes that are going on. Up to this day, opinions diverge considerably, such as the Copenhagen interpretation, many worlds, etc. That is the end of our presentation. Thank you.
So one of the questions that was posed was in one of our previous slides. What exactly is the Hamiltonian operator? And it's basically just the sum of the kinetic energy and the potential energy in a system.
Hello, today we'll be presenting on flame tests and its related applications. We will be using the 5W1H approach for this presentation. So what are flame tests? Flame tests are used to identify the presence of metal ions in a compound. However, not all metal ions give flame colors. Moreover, some metal ions give similar colors, subject to the judgment of the person carrying out the experiment. The flame test only gives qualitative information and not quantitative data on the proportion of elements in the sample. Quantitative data can be obtained by the related techniques of flame photometry or flame emission spectroscopy. Some colors of the flames are more intense than others. Cal sodium's color is more intense than that of potassium. Hence, the flame test should not be used in isolation to confirm the identity of the metal ion in the compound, as the compound might not be pure. This is because some flame colors are so strong that they can mask other colors. If we heat the sample of solid potassium chloride, which will give a lilac flame, and there is a small amount of sodium chloride impurity present, we will see only a yellow flame instead of a lilac one. When do we use the flame test? We do the flame test when we are trying to figure out the identity of the metal cation in the compound, or at the very least, narrow it down to specific ions. It works best with group 1 metal ions and does not work with some metal cations. Lastly, anions of the compound do not affect the test, which will be delved onto later.
Next, who the flame test? In 1822, John Herschel noticed emission spectra lines while passing light from different colors of flame through a prism. 4 years later, photographer William Fox Talbot noted, "A glance at the prismatic spectrum of a flame may show it to contain substances which would otherwise require a laborious chemical analysis to detect." Talbot later used it to distinguish between lithium and strontium compounds, both of which emit red flames, but with different spectra. But impurities in the samples available at the time made it difficult to prove, since multiple spectra would be pronounced simultaneously. So there had never been a careful systematic approach to such studies before Bunsen and Kirchhoff teamed up in 1859. Bunsen came up with the idea of using filters to block intense colors, like the yellow of sodium compounds, to better detect less intense colors of light emitted by other elements, such as the violet hues of potassium. Kirchhoff then suggested improving on this method by adapting the Herschel-Talbot method of passing the light through a prism. Together, they devised an instrument based on this principle, the spectroscope. All right, next, wear the flame test. Where else other than the lab, bro? And make sure to take note of your laboratory safety. Next, how the flame test. Firstly, dip a clean wire loop into a solid sample of the compound being tested. Then put the loop on the edge of a blue flame from a Bunsen burner. Finally, observe and record the flame color produced. You can also use a wooden splint or a cotton swab, but it will ignite when placed into flame and need to be replaced each test. Why the flame test? Why does the flame test work? Well, if you excite an atom or an ion by very strong heating, electrons can be promoted from their normal unexcited state into higher orbitals. As they lose energy, they fall back down to lower levels, either in one go or in several steps, and that lost energy is released as a photon of a specific wavelength. Each of these jumps involves a specific amount of energy being released as light energy, and each corresponds to a particular wavelength or frequency of light. As a result of all these jumps, a spectrum of lines will be produced, some of which will be in the visible part of the spectrum. The color you see will be a combination of all these individual colors.
For example, if you put sodium chloride which contains sodium ions into a flame, some of the sodium ions regain their electrons to form neutral sodium atoms again. A sodium atom in the unexcited state has the structure 1s2, 2s2, 2p6, 3p1. When heated, the electrons gain energy and can be excited into any of the empty higher energy orbitals, 7s, 6p, 4d, or any other, depending on the amount of energy a particular electron happens to absorb from the flame. Because the electron is now at a higher and more energetically unstable level, it falls back down to the original level, but not necessarily in one transition. Sodium's familiar bright yellow, orange-yellow flame color results from promoted electrons falling back from the 3p1 subshell to the normal 3s1 level subshell. As the energy gap between subshells is different for every metal, the exact sizes of the possible jumps in energy terms vary from one metal to the other. This means that each different metal will have a different pattern of spectral lines and therefore a different flame color. So, when can we use the flame test? Some metal cations and anions don't produce visible light because the thermal energy from the Bunsen burner is not enough to excite the electrons of these elements. Or electrons that are excited emit light that is not in the visible light section of the electromagnetic spectrum. Thus, there is little to no flame color produced. However, sometimes you can still see the influence of the anion used in the emitter spectrum. For instance, copper bromide will yield a blue-green flame, while copper sulfate will have a green flame. Comparatively, the flame test works best with group 1 metals due to their low excitation energies. Some related concepts like qualitative analysis, which is figuring out the metal through testing and observation, is important in the flame test. Knowledge of the reactivity of metals, as well as the electronic configuration is also related. Orbitals and their related energy levels must also be known.
So, moving on to the Q&A. A question was asked regarding why colors within the same element on the spectrum have different intensities. The intensities of the colors, i.e. the brightness, is proportional to the number of photons emitted and not the energy released. As electrons will tend to fall in particular energy levels, this results in higher intensities of some colors. Another question was asked regarding why the intensity of flames between elements is different. Different elements have different quantities of photons and neutrons, which results in different energy levels between subshells. The number of electrons that jump up and down the energy levels would naturally be different if the amount of energy supplied is the same. Another question asked was what happens if the element has only one visible quantum shell, like hydrogen. Even though hydrogen only has one electron shell, its electrons can move up to higher energy levels as long as enough energy is supplied. Hence, it emits multiple colors on the emission spectrum. With hydrogen, the emission spectrum is pretty straightforward because there's only one electron to emit photons. So you have the 2s to 1s transition line, the 2p to 1s transition line, and so forth. It should be noted that the electron won't always drop all the way to 1s. And so what type of electrons can be excited? Any electrons can be excited out of its original energy state into a higher state. However, we only view valence electrons or those close to valence energy transitions. This is because core electrons require a large amount of energy, such as from an X-ray, in order to be excited, owing to the fact that they are tightly bound to the nucleus. Thank you for listening to our presentation.
Hello, today Gabriel Reuben, Ling Bo, and myself Reuben from 23S6G will be presenting on the quantum mechanical model of the atom, more specifically the wave-particle duality of electrons and quantization of photons. Let us first begin with the history of the model for an atom. The first model proposed by Dalton was the plum pudding model. In this model, atoms are spherical clouds of positive charge with electrons scattered throughout it. Whilst this model was elementary, it already showed that electrons are a component of atoms, and the atoms themselves have no net positive nor negative electric charge. This model was then improved on when Rutherford proposed the nuclear model. According to Rutherford, atoms are mostly empty space, with a dense positively charged nucleus and electrons moving randomly in the space around it. What Rutherford therefore got right is that positive charge is localized in the nucleus, and the atoms are mostly made up of empty space. Bohr then moved on to propose the planetary model. It is called the planetary model because, under Bohr's model, electrons are arranged and move in specific concentric circular orbits around the nucleus just like planets do. Whilst this has now been proven to be wrong, Bohr did correctly quantize electron energy and proposed that there are stable electron orbits. This model, however, would undergo yet another revolution as more scientific discoveries are made, and it starts off with light. Light, as you may know, is electromagnetic radiation, meaning that light is a wave in an electromagnetic field. Light does tend to behave in a wave-like fashion, such as reflection, refraction, and diffraction. However, it is also similar to waves of water, as it can display signs of interference, shown in the famous double-slit experiment. In the double-slit experiment, monochromatic light that comprises of a single wavelength is shone through two slits, but instead of observing two beams of light as expected, a wave-like pattern which demonstrates both constructive and destructive instances of interference can be clearly seen.
However, such a simplistic understanding of light as merely a wave will ultimately be challenged by the physicists Rayleigh and Jeans in what we know today as the ultraviolet catastrophe. Rayleigh and Jeans try to describe blackbody radiation using classical physics, something which ultimately collapsed because the blackbody radiation predicted by classical physics agrees with experimental results at low frequencies, but strongly disagrees at high frequencies. Their theory predicted that blackbodies will emit an infinite amount of energy at high frequency, something which we know is impossible by the law of conservation of energy. This suggests that there were fundamental flaws in our understanding in classical physics, challenging the notion of light as merely a wave as we knew at that point in time. The solution to this problem was unintentionally proposed by a German theoretical physicist Max Planck, who introduced the assumption that energy is radiated by the black body in discrete packets or quanta, in the sense that high-frequency packets are only released when enough energy can radiate outwards, rather than infinitely, as Rayleigh and Jeans had suggested. Planck thus propounded the theory that light is quantized, but it was Einstein who solved the problem by postulating that Planck's packets of energy suggested that light was not just waves, and were made of real physical particles called photons, giving rise to our understanding today of light as particles in the wave-particle duality. This ultimately serves as the building blocks for quantum mechanics, changing our understanding of the world and the atom as we know it. Since quantum mechanics has changed our understanding of the atom, it will now be useful to look at the history of the atom itself. So just as how quantum physics actually builds upon classical physics, the many models of the atom all build upon one another, and have all contributed to our understanding of the atom today in their own manners. So the plum pudding model recognized electrons as being part of atoms and that atoms had no electric charge. The nuclear model of atoms postulated that positive charge was localized in the center of the atom called the nucleus, and that atoms are made up of mostly empty space. The planetary model furthered our understanding of the electron by suggesting that electrons were found in stable orbits or stable energy levels around the electron, though it was flawed in suggesting that electrons were in fixed positions around the atom. This flawed understanding of the atom was ultimately corrected by the quantum model, which brought light to the fact that electrons move in waves, and that the exact position of electrons were unpredictable, and they instead exist in electron clouds, which were merely clouds of probability.
Moving on, let's talk about the nucleus, the heaviest central part of the atom. Have you ever wondered what holds the nucleus together? As we all know, the nucleus is made up of protons and neutrons. We also know that protons have a positive charge and like charges repel. So, why does the nucleus fall apart under the repulsion of positively charged protons? Well, this is because of the strong interaction. Not only does the strong interaction hold the nucleus together, it also holds quarks, small particles that make up the protons and neutrons, together. The strong interaction is stronger than weak interactions. While this might sound like common sense, note that the electrical repulsion between positively charged protons are a form of weak interaction. To understand this, think of neutrons as a really strong glue that effectively binds protons together even though protons want to move away from one another. This explains why in heavier atoms, the neutron to proton ratio is higher as there is more inter-proton repulsion. Next, why does strong interaction exist? Just like how electric force acts on electrically charged particles, the strong force acts on particles with color charges. Color charges can be blue, green, red, or their anticolors. To be color neutral, particles should possess a color and its anticolor, all three colors, or all three anticolors. However, do not confuse color charges with the colors we see. Color charges have just unfortunately been assigned the name color, but are in fact very different from actual colors. Gluons carry color charges between quarks. Both gluons and quarks have color. However, gluons are also colored, and so more gluons carry color charges between gluons. This cycle repeats, creating a string of gluons between quarks that tie quarks together. Hence, no quark can exist singly. It must be tied to its antiquark or two other quarks with gluons, as in the case with hadrons such as protons and neutrons. Next, let's talk about electrons. Do you know that electrons can pass through the nucleus? As electrons are not made up of quarks, they are unaffected by the strong force. They are negatively charged particles that wouldn't quite be pinned down. They were shown by the double slit experiment to behave like a wave, just like photons. We now understand electrons as standing waves in fixed orbits around the nucleus. As measuring each electron's momentum would affect its position and vice versa, it is more meaningful to predict the probability of finding an electron at a particular location than to find the exact trajectory of every electron. Electron orbitals are defined as regions where there's more than 90% chance of finding an electron. Electrons hold different energy levels depending on which orbital they occupy and what atom they are in. This gives rise to different ionization energies of atoms depending on the energies of electrons removed. A somewhat obvious but important fact is that you cannot tell one electron apart from another. Electrons, just like neutrons and protons, are fermions. Pauli's exclusion principle states that no two identical fermions can have the same quantum state. In simple words, this means that no two electrons can be at the same place at the same time. And that is what an electron is.
Now we know how electrons are waves and not particles, it makes more sense why they can exist around the nucleus at discrete levels. These are the quantum shells, which we are familiar with. Orbitals should not be recognized as the path of the orbit of the electrons, because the electrons don't actually orbit, they aren't individual particles. Rather, they are the probability density, the space where you have a more than 90% chance of finding an electron if you were to measure it. This also explains phenomena like dipoles, right? It's not like there's actually an electron always at the left or the right of the nucleus, which creates the dipole moment. Rather, you're more likely to find an electron there if you were inclined to measure it. So in this sense, it's a cloud of probability density. You can see on the screen the orbitals for S, P, and D. Note there are 2D orbitals. Each of these orbitals holds a single pair of electrons, one with upspin and one with downspin. As you go from S to P to D to F, you might note that these orbitals become increasingly complex in their shape. The shapes are derived from Schrödinger's equation, and this becomes increasingly complex to solve as the energy increases. However, observations suggest that these models are fairly accurate. So this is a simple illustration for how you should visualize these orbitals around the nucleus. Before we wrap up, here's a quick aside on hybridization. Why are molecules the shape that they are? For instance, why do we have tetrahedral-shaped molecules and not some other shape? How is it even possible for a molecule to have a triangular shape if the p orbitals aren't triangular? Hybridization occurs when an atom bonds using electrons from both the s and the p orbitals, which of course creates an imbalance in the energy levels of electrons. And this imbalance is one which the atom fights against. So to equalize the energy levels, the s and p orbitals combine to create a hybrid orbital. Once again, this is in our syllabus in the future, so you can look forward to that, I guess. So we've come to the end of our presentation. Thank you for listening.
Hi everyone, I'm Joanne and we'll be presenting on Slater's rule and physical periodicity. Firstly, the shielding effect. The shielding effect describes how electrons closer to the nucleus shield the electrons further away from the positive charge of the nucleus. Each electron experiences both the electromagnetic attraction from the positive nucleus and the repulsion forces from other electrons in shells from 1 to n, which causes the net force on electrons in outer shells to be significantly smaller in magnitude. It contributes to the explanation of why valence shell electrons are more easily removed from the atom.
Hi, I'm Guan Yi, and I'll now be presenting about the Slater's rule. So what exactly is the Slater's rule? As we all know, the effective nuclear charge is found by taking the nuclear charge, which is the number of protons inside the nucleus, and subtracting it by the shielding constant. The Slater's rule is a guide of determining the shielding constant and therefore the effective nuclear charge. So, how do we determine the effective nuclear charge for s and p electrons by applying the Slater's rule? First, we write the electronic configuration for the atom in the way as shown in the slide. Next, we assign the values, where n is defined as the outermost shell. For each of the remaining electrons in the m shell, we assign a value of 0.35. for each of the electrons in the n-1 shell, we assign a value of 0.85. Finally, we assign a value of 1.0 for each of the electrons present in the rest of the inner shells. As an example, let's look at a fluorine atom. Its electronic configuration is written as 1s2, 2s2, 2p5. To calculate the effective nuclear charge, we take the nuclear charge, which is 9, and subtract it by the shielding constant. As we can see in the diagram, we have 6 other electrons in the outermost shell, and 2 electrons in the n-1 shell. Hence, we get a value of 5.2.
Hi, I'm Ziyu. I'll be presenting on physical periodicity and atomic radius. There are two different types of atomic radius. The first being covalent radius, where we simply halve the distance between the nuclei of the two atoms that are bound to each other in the molecule. The other type of atomic radius is the van der Waals radius, where we halve the minimum distance between the nuclei of the two atoms of the element that are not otherwise bound by covalent or metallic interactions. So hence this is mostly used to determine the atomic radius of noble gases. As you can see in the periodic table shown here, across the period, ionization energy and electron affinity will increase, while atomic radius will decrease. While down the group, electron affinity and ionization energy will decrease, while atomic radius will increase.
Hi, I'm Jiaxin. Now I'll be explaining about the trends of atomic radius down the group and the period. Down the group, the atomic radius increases. This is because as the number of quantum shells increases, the outermost electrons are further away from the nucleus, hence the atomic radius increases. Across the period, atomic radius decreases. The nuclear charge increases due to an increase in the number of protons in the nucleus. Shielding effect remains relatively constant and the effective nuclear charge increases, leading to the outermost electrons being pulled closer to the nucleus. Next slide. So, the first anomaly is the noble gases. Noble gases appear to have a much larger atomic radius, as their atomic radius is defined by their van der Waals radius, rather than their covalent radius, because most noble gases do not form compounds. The second anomaly is the transition elements. The atomic radius of transition elements is relatively invariant. Nuclear charge increases due to the increasing number of protons for the transition elements across the period. As electrons are added into the inner 3D subshell, it contributes to the overall shielding effect, and the effective nuclear charge remains relatively constant. The last anomaly can be seen in the lanthanides, and it's known as the lanthanide contraction. Due to the poor shielding effect of the 4f electrons, the lanthanides have a smaller than expected radius. You can see the electronic configuration of lanthanides below. Thank you for listening to our presentation.